Alright, morning everybody. Welcome back to Math 105. Plan for today is we're going to finish our discussion of Standard 9 and talk through a couple more examples of reductio ad absurdum. I got my usual office hours today at 10 o'clock and from 2 to 3. Still got a few time slots open if you'd like to come by and talk about anything. And as far as homework goes, I did post the Standard 9 quiz. Since I don't want to have to make you have to do anything over the break, it won't be due until Tuesday evening after the break. And I'll remind you Monday after we get back for that. And also, have a good break. And if you're traveling anywhere, especially, make sure you practice good COVID safety protocols during the break. Anybody have any questions or comments before we get started today? Yes?
Do you have an extra packet for Standard 9?
Ooh, I did not bring any with me. The Standard 9 packet is up on Blackboard though.
If you want to move over here, you can share mine.
It's okay, I can just read it. It's okay.
Sure.
Yeah, it's fine. Thank you.
There's not going to be too much stuff from the packet itself, pre-written stuff in the packet itself for what we're going to be doing today. Any other questions? Okay. One day, several people were asked, what is 2 times 2? The engineer whips out his graphing calculator, presses a bunch of buttons, and finally announces 2 times 2 is 3.99 plus or minus 0.01. The physicist consults his technical references, sets up the problem on his computer, and announces 2 times 2 is somewhere between 3.98 and 4.02. Mathematician thinks for a moment and says, I don't know what 2 times 2 is, but I do have a proof that an answer has to exist. The philosopher smiles and says, what do you mean by 2 times 2? The logician replies, you're going to need to define 2 times 2 more precisely. The sociologist says, I don't know what 2 times 2 is, but it sure was nice talking about it. The biologist says 2 times 2 is a polygamous mating system. And finally, the med school student says 2 times 2 is 4. The others all look at her astonished and ask, how did she know that? She answers, oh, I memorized it. Okay, so we introduced the idea in last class of reductio ad absurdum, which is kind of a proof technique. Make sure I'm on the right page of my notes. Reductio ad absurdum, or RAA for short, where the whole idea behind this proof technique is we have a statement P that we'd like to prove must be true. The idea behind reductio ad absurdum was we assume, to prove that P is true, we start by assuming P is false. And then show that it leads to a logical contradiction. Hello, newcomers. So, we looked at an example of using reductio ad absurdum in our last class, where we actually proved that no number can be both even and odd at the same time. And our strategy was we used reductio ad absurdum. We assumed the opposite of what we wanted to prove. We assumed there is a number that is both even and odd. And then eventually we were able to say, well, based on that fact, we know that we could take 2 counting numbers, subtract them, and get a half, which is something that's impossible. You shouldn't be able to subtract 2 counting numbers and get a fraction. And that was our idea behind how we could show no number is both even and odd, assume the opposite, and then show something goes horribly, horribly wrong. So today, I wanted to focus on looking at a couple more theorems. And these two theorems I want to talk about today, these are not going to be theorems that I would expect you to be able to figure out on your own. These are going to be longer, more complicated proofs. These are not going to be theorems that I ask you to prove on the test or anything, but I think they are good kind of historical examples of how reductio ad absurdum was kind of used in the past to prove these huge mathematical results. And in particular, what I want to do today is talk about proof that square root of 2 can't be written as a fraction, and a proof that there are infinitely many prime numbers. So to start with, let's write a definition down. I'm going to say that a number n is called rational if n is equal to a over b for some counting numbers a and b. So in other words, we call a number rational if it can be written as a fraction. And so one example of something that I would consider to be rational would be something like 1/2, because it can be written in the form counting number 1 divided by counting number 2. What do you think? I already spoiled my answer. I was supposed to write it over here and then make you guess which column it went in. 1.5. 1.5. Do you think this would be a rational number or an irrational number? Meaning, can this be written as a counting number divided by another counting number, or would it not be able to be written in that way?
It's rational because you could write it as 3.
Yeah. Even though 1.5 isn't written as a fraction the way it currently looks, it is equal to something that can be written as a fraction. And so I would say that that's a rational number. How about the number 2? Is that something that would be rational?
It's the same as 2 over 1. So yes.
Yeah. Any counting number is automatically going to be rational because you could just write that counting number as itself divided by 1. And so 2, which you could write as 2 over 1, or 4 over 2. There's lots of ways of writing it as a fraction, but anything you can write as a fraction is going to be rational, even if it doesn't look like a fraction form from the get-go. So, anybody think of any numbers that you might consider to be irrational? Numbers that can't be written as a counting number over another counting number. Pi, I would say, is the most famous example of that. It's not easy to prove that pi is irrational. It actually takes a lot of work to show that pi can't be written as a fraction. But pi would be one of these irrational numbers. Another kind of famous one, if you've ever taken a calculus class before, would be e, from the exponential function e to the x, which is about 2.71 blah, 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 would be another example. And the first number that was ever shown to be irrational, but can't be written as a fraction, the one I want to look at in an RAA proof today, it's going to be square root of 2. So here's going to be our theorem that square root of 2, or let's not write this as theorem quite yet. Let's write this as a claim. I claim that square root of 2 is an irrational number, i.e. square root of 2 can't be written as a fraction. So this is a proof that's attributed to Hippasus of Metapontum. I'm probably horribly butchering that pronunciation, and if so, I'm sorry. And this is kind of the famous result that which, during the time of the ancient Greeks loved counting numbers. To them, counting numbers was everything in math. They literally had, if you go back to Pythagoras from Pythagorean theorem, Pythagoras literally led a cult about how awesome the counting numbers are. And so when Hippasus came and said, hey, I have this number, square root of 2, and I think it can't be written as a counting number. This is kind of the fake. There's no way of knowing if this is actually a true story, but this is kind of the legend, how the legend goes. The Pythagoreans were so enraged that someone would dare speak up against their cult of the counting numbers that they took him out onto a boat, threw him overboard, and drowned him for daring to proclaim that something couldn't be written as a fraction using just counting numbers. Probably not actually a true story, but it makes sense given what we know about how crazy some of the ancient Greeks were, and so we like to still say it. So I'd like to prove this claim using reductio ad absurdum. So we're going to prove that this claim is true by assuming it's opposite, by assuming it's not true and showing it leads to a logical contradiction. So with that in mind, treating this as a reductio ad absurdum proof, what do you think might be the first line, could be the first line of our proof, if we want to use this method?
Assume the square root of 2 is a rational number.
Yeah. So we're going to assume the opposite of what we want to show, and the opposite of square root of 2 is irrational would just be square root of 2 is rational. Or irrational, if you will. Let's do that. We're going to assume that square root of 2 is a rational number. Well, then by definition, since square root of 2 is rational, that would mean square root of 2 has to be equal to some a divided by b for some counting numbers a and b. So we're assuming the opposite of what we want to show, and then just can apply our definition of what does it mean for square root of 2 to be rational. It's just going to be some fraction. Here's going to be a little bit of a tricky bit. We're going to assume that a over b, that a and b have no common factors, because if they do have any common factors, it can cancel them out. So basically what that means is we can assume that a over b is written in simplest form. So if we had something like a is equal to 4 and b is equal to 6, how could we write the fraction 4 divided by 6 in simplest form? What could we do to sort of cancel things out?
2 over 3.
It's 2 over 3. So how do we get from 4/6 to 2/3?
Dividing both of them by no common factor 2.
Yeah. So we noticed that we could cancel out a factor of 2 in the top and bottom of the fraction. And so we could take something where 4 and 6 that have a common factor of 2 in them and just divide out by 2 in the top and bottom And we end up with something 2 over 3, where 2 and 3 have no common factors. There's nothing to simplify. So as part of our proof, we're basically just saying square root of 2 is a over b. We can just assume that a over b is a simplified fraction, that they have no common factors that we could cancel out from the top and bottom. And this is going to be important for us later on, because later on, what we're ultimately going to show is that a over b have to have a common factor, which contradicts our claim that they have no common factors. That's going to be our contradiction later on in the proof. So we've assumed a and b have no common factors. So we could say that since square root of 2 is equal to a over b, what I'm going to do is I'm just going to do a little bit of algebra and multiply both sides of this by b. If square root of 2 is equal to a divided by b, then what should a be equal to?
B times square root of 2.
B times square root of 2. So we know that given our a and b, a has to be equal to b times the square root of 2. And what I want to do now is I want to square both sides of this. And so if we square the left-hand side, we'll get a squared. If we square the right-hand side of this equation, we'll get b squared times square root of 2 squared, which is just going to be 2b squared times 2. Or 2b squared, if you will. So here we just squared both sides of the equation, a equals b square root of 2. And now, we could say that since a squared is equal to 2 times the counting number b squared, what does that tell us has to be true about a squared? If we know that a squared is equal to 2 times this counting number b squared. Since a squared is a multiple of 2,
We know that a squared is even.
a squared has to be an even number. It's even because it's a multiple of 2. Using some stuff we've already proven earlier in the packet, we can say that since a squared is even, a has to also be even. That's kind of a property that we've seen before, that like if we have a number squared and it's even, then the number itself, a, has to also be even. So a is even. And now I'm going to use the definition of what it meant for a to be even and say that thus a is equal to 2n for some counting number n. Again, just applying the definition of what it means for a to be an even number. And now we can say that since a is a multiple of 2, a is equal to 2n for some counting number n, we can go back up and use this equation right here, that a squared is equal to 2b squared, and say that 2b squared, which we said was equal to a squared, also has to be equal to the expression 2n quantity squared, which in turn is going to be equal to 4n squared. So we're almost through everything we need to find our logical contradiction we have that 2 times b squared has to be equal to 4 times n squared. But since 2b squared is equal to 4n squared, what does that tell us about b squared? What would we get if we took both sides of our equation, in other words, and divided both sides by 2?
B squared is an even number.
B squared is equal to 2n squared, which is a multiple of 2, and then b squared would be an even number. Yeah. Skip ahead a step from what I was going for. So yeah, that's exactly right. Since 2b squared is equal to 4n squared, we could just divide both sides by 2 and say b squared has to be equal to 2n squared. And then, since b squared is a multiple of 2, as we say, b squared has to be an even number. So b squared is even. B squared is even because it's a multiple of 2. But if b squared is even, what does that tell us about b?
B's even as well.
Yeah, b squared is even, b has to be even. So b is a multiple of 2. And I think we're ready to arrive at our contradiction. And this, in particular, is going to be the piece that we're contradicted. We know that a and b can't have any common factors. But from the work we did over on this board, I think we've shown that a and b do have a common factor. So from what work we've done here, what would be a number that would be a common factor of both a and b from the work that we've done? 2. A is an even number, so a has to be a multiple of 2. B is an even number, so b has to be a multiple of 2. Therefore, a and b are both multiples of 2, which is going to contradict this piece right here where we assumed a and b have no common factors. And then a and b are multiples of 2. Contradicting that a and b can't have any common factors. And thus, we've contradicted our original claim that square root of 2 is rational. Thus, square root of 2 can't possibly have been rational to begin with. Square root of 2 is an irrational number. Thus, square root of 2 must have been irrational to begin with. This is a very lengthy proof, but it ultimately boiled down to the idea of we want to show square root of 2 is irrational. We assumed the opposite of that. We assumed that square root of 2 is rational, and then showed that if the assumption that square root of 2 is rational is true, we end up arriving at a logical contradiction somewhere. Namely, a and b have no common factors, but a and b also have a common factor of 2. We show something that can't possibly happen happens. And so, ultimately, our claim that square root of 2 is rational must have been absurd, impossible. So square root of 2 is irrational again. By the way, when I say absurd, I don't necessarily mean it's ridiculous, and anyone who could possibly think square root of 2 is rational is an idiot. That's not what I mean by absurd here. Absurd just basically means impossible. And so that's kind of where reductio ad absurdum comes from. It's basically proof by contradiction. We have shown something that's impossible to happen happens, and therefore our original assumption must not have been true. So let's stop for a second, and I just want to see what questions do you all have about this? As a general reminder, I'm not going to make you like prove this on an exam or something. I might ask you questions about this proof. But this is the sort of proof that took ancient Greeks a very, very long time to come up with. I would not expect you to be able to create a proof this long or anything on the fly. If I ask you to prove something on the standard 9 quiz, it'll be something along the lines of what we were doing our first day, probably of show that if A is even and B is odd, then A plus B is odd, something like that. But this has the same basic structure. We made an assumption at the start. We showed something happened. In this case, that we have a logical contradiction. And that's going to be the essence of any proof. You make your assumptions at the start, then you show something happens. Let's do another one. So that was a proof that was attributed to Hippasus. The next theorem is going to be one that's attributed to Euclid, that there are an infinite number of there are infinitely many prime numbers. So before we start stating our theorem, we need to know what a prime number is. Because it's always good to have these carefully written definitions for when, in order to be able to prove anything. So, new definition is going to be a counting number n is called prime if n has no factors other than itself and 1. So numbers prime if it has no factors other than itself and 1. So what would be an example of a number like this that has no factors other than itself and 1?
2.
2 would be a great example. We could say that 2 is going to be prime since 2's only factors are 2 itself and 1. In fact, 2 is going to be the only even number that's prime. Any other even number would have a factor of 2, which is a different factor from itself and 1. Some more prime numbers would be like 3. Another one would be 11. Both also going to be numbers that are only multiples of themselves and 1. What would be an example of a number that's not prime? Something that has factors other than itself and 1.
15.
15? What would be a factor of 15 other than 15 and 1?
3 or 5.
Yeah, 3 and 15 has 2 other factors of 3 and 5. Since 15 also has factors of 3 and 5. Another example would be something like 4, since 4 has a factor of 2. And so any number, based on what its factors are, will be able to be classified as being prime or non-prime. Except for one, but one is weird. So we don't count one. And of course, so Euclid is kind of attributed with coming up with this claim that we could also prove as an example of a reductio ad absurdum proof. Euclid claimed and was able to prove there are infinitely many prime numbers. So in other words, Euclid claimed you would never stop, no matter how far out you go in the number line, you're always going to find more counting numbers that have this prime property. You're never going to run out of prime numbers, so to speak. That 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, you can keep going and keep finding more and more prime numbers no matter how far out you look. There's an infinite supply of them. Which is not entirely obvious, I don't think. How do we know we can't eventually run out of prime numbers if we go out far enough? And so what Euclid did was he wrote a proof using the method of reductio ad absurdum to actually show that there have to be an infinite number of prime numbers. So if we wanted to write this as a reductio ad absurdum proof, what might we want to assume at the start? So what could we do as sort of our starting assumption if we want to show that there are an infinite number of prime numbers? And we want to show that if that's false, we would arrive at a contradiction.
There is a finite number of
Yeah.
numbers.
We're going to assume that there's a finite number of prime numbers, and then show at the end of our proof that that gets into some hot water mathematically. Let's assume there are only finitely many prime numbers. And I'm just going to call them P1, P2, up to P sub n. So we're going to assume that P1 is the first prime number, P2 is the second, etc., etc. And we're going to assume P sub n is the last prime number. But if there's only a finite number of them, then we should be able to, in theory at least, just list them all out. P1 through some P sub n. And now, what I'm going to do in order to prove that we have a contradiction is I'm going to show we have another number. There has to be another prime number that's not in the list already. So we're assuming that these are the only prime numbers. And then our contradiction is going to be, if these are the only prime numbers, I can give you one more. Which shouldn't be able to happen if this is the entire list of prime numbers already. And the number I'm going to show has to also be a prime number. It's going to be, I'm going to call it P, which is going to be what I get from taking all of these n prime numbers, multiplying them together, and adding 1. So here, all that I've done is I've said I'm defining a new number that's taken from multiplying all of these prime numbers together. Put little dots in here so you can see it's multiplication. We've multiplied them all together and added 1 to our final result. And I claim this is going to be a new prime number that's not in the previous list. So if we wanted to show that this new number p is prime, what would we have to do? We used the definition of prime number and we wanted to show that the number p here had to satisfy this definition of being prime. What would we have to show about p?
It has no factors other than itself and one.
Yeah, we need to show that it has no other factors other than itself and 1. And in particular, we can do that just by showing it has no other prime factors. So we will show p has no prime factors. So one nice thing about saying, hey, we have a list of all the prime numbers, p1, p2, up through pn. The nice thing about having such a list is, well, here are all the primes. So if we want to check to see if p has no prime factors, then all we have to do is to just show p1 isn't a factor, p2 isn't a factor, up through p sub n. If none of these numbers in the list are prime factors, then p can't have any prime factors at all. So I'm going to say that we know p1 isn't a factor of p, because if it was a factor of p, if p1 was a factor of p, meaning if, let's say, p is equal to p1 times k for some counting number k, because that's what it means for p to have p1 as a factor. It's just p1 we could multiply by some counting number and end up with p. Then what would happen is that we would have p, which is equal to, actually instead of p, let's say 1, which should be equal to p minus the product of all of our prime number factors. And this just comes from taking this equation right here and subtracting this big product from both sides. We subtract p1 times p2, etc. from both sides, we would have 1 is equal to p minus this big thing. If 1 is equal to that, well, then we could replace p with p1 times k, and we'd get p1 times k minus p1 times p2, blah, 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 up to pn. And what we would be able to do is we'd be able to factor out a p1 from the right-hand side, and we'd get k minus p2, p3, all the way up to p sub n. And that can't happen why do we know this can't happen? Because if we showed, what we've shown is that p1 is a factor of 1. And does 1 have any prime factors? 1 doesn't have any counting number factors other than itself. And so I would say this would contradict p1. This would make 1 have a factor of p1, which can't happen. So in other words, P1 can't be a factor of P, because if P1 was a factor of P, we would be able to show that P1 is also a factor of 1. And that can't happen because 1 has no prime factors. If you notice, I just did something very sneaky. I just used a reducto ad absurdum proof as part of our bigger reducto ad absurdum proof. I showed P1 can't be a factor of P using reducto ad absurdum. I assumed if P1 is a factor of P, we would arrive at a contradiction. So we just used reducto ad absurdum within a proof of reducto ad absurdum, creating reducto ad absurdum sections, which is madness. But it actually is okay. And something that doesn't happen often, but does happen on occasion, is you have multiple reducto ad absurdum arguments occurring within the same proof. So what did we just show? We just showed that P1 can't possibly be a factor of P. And here's the thing. We just showed P1 can't be a factor of P, but we could really make the exact same argument about P2, P3, etc. And if we just replace P1 with P2 in this whole argument, then that same argument would show P2 isn't a factor of P. P3 can't be a factor of P by basically the same argument. In general, none of these primes, P1 through Pn, can be factors of P by just repeating the same basic argument over and over, just swapping out P1 with whichever other prime in the list you want as needed. So by similar arguments, none of the prime numbers P1, P2, up through P sub n can be factors of P. And this is going to be our contradiction, because we just showed that the number P has no prime factors. And how many counting numbers are there that have no prime factors?
I guess you could keep doing this, make P the last one in the set, and then do another one on top of that so it's infinite.
Yeah, the problem is, well, there's a couple ways you could think about this. So the way you're thinking about this is P itself has to be prime, and therefore this wasn't the entire list of prime numbers to start with, which is a contradiction. We assumed it was. The other way you could make a contradiction is to say if P has no prime factors, the only counting number with no prime factors is the number 1. And P very clearly cannot be the number 1 because if P was 1, then this thing would have to be 0, and this did not multiply out to be 0. 0 is not a prime number, so we can't multiply all of this out and get 0. I'll say this. I'll go with your contradiction. Thus, P is a new prime number, which can't possibly happen. P is a new prime number which cannot possibly have been in the list. P1 through Pn contradicting our claim that that list P1 through Pn is all of the prime numbers. And there's our contradiction. We assumed that we have a list, P1 through Pn, of all the prime numbers, and we contradicted that that's all of the prime numbers by being able to construct a new prime number, this number P. We know, by the way, P can't be equal to any of the previous ones because P has to be bigger than all of these other prime numbers. If we multiply them all together and add 1, we have to get something that's bigger than everything in this list to start with. And then one more line to finish it up. Thus, there can't be a finite number of primes, there has to be an infinite number of primes. Same basic idea as the last couple of reductio ad absurdum proofs. We started by assuming the opposite of what we wanted to show. We want to show there are infinitely many. Well, let's assume there's only a finite number of primes. And then we do a whole bunch of work that ultimately shows we arrive at a logical contradiction. Because we assume there's P1 through Pn are the only primes. Well, tough luck. It turns out that couldn't possibly happen because we could always construct a new one by taking all the previous primes, multiplying them together, and adding 1. We've assumed the opposite of what we wanted to show, and then arrived at a logical contradiction. I wanted to introduce to you some examples of reductio ad absurdum being used, because it's going to be a tool we use very often in the second half of the semester when we're looking at geometry. There's going to be lots and lots of statements about triangles and circles and squares, etc., that we want to be able to prove. And the only tool that we're going to have, and oftentimes the only way we'll be able to prove these sorts of statements, is by using the principle of reductio ad absurdum. So this sort of argument is going to be common. Assume the opposite of what you want to show bad things happen. Show something logically happens that can't possibly happen. And again, on the standard 9 quiz, I'm not going to ask you to write out these whole proofs because I assume you would just copy it verbatim from your notes. But and I know I went a little bit fast, and you likely didn't catch or didn't understand everything that I said. But I wanted to give you a sense for how important this concept of reductio ad absurdum can be in proving these mathematical claims. Any questions or comments? In that case, have a nice break. When we come back on Monday after break, we're finally going to start talking about Euclidean geometry. And we'll be starting in Standard 10. So have a good break, everybody. I will see you all on Monday. Yes?
So should we bring our books then to next class?
You don't need to bring the books right away. I'll tell you when you need to start bringing your books, and it won't be until we actually start proving some of Euclid's propositions. But we're going to start talking first a lot about what were Euclid's definitions for things, what was Euclid trying to do historically. You won't need them.
Thank you.
No problem.
Thank you. See you next week.
You as well. Oops.